Okay, so today we're going to incorporate section 3.5, just because it also deals with limits at infinity into this. So we are going to jump just to that section in the textbook. So we have, so it says line y equals L is we're going to be dealing with horizontal asymptotes, or not so much horizontal asymptotes in terms of using them, but we're going to relate them to how we figure out what a horizontal asymptote actually is. So the line y equals L is a horizontal asymptote of the graph of f if the limit as x approaches negative infinity of the function f of x equals uppercase L, or the limit as x approaches positive infinity is equal to L. So note that from this definition, a graph can have at most two horizontal asymptotes, one from the right and one from the left. Some properties here that are going to be used, but basically we had learned in section 1.5 with one of the properties, I think it was the third one, that anytime you have a number divided by a variable in terms of the function itself and you are approaching infinity, the value is equal to 0. So that is where theorem 310 comes from. So it says if r is a positive rational number and c is any real number, then the limit as x approaches infinity or x approaches negative infinity of c, again, c is a number, over a variable raised to any power is always equal to 0. So any constant over a variable, when you take the limit as it approaches infinity, not any other number, it has to be approaching infinity, but you get a 0 for that value. So if we look at example 1, we've got multiple things going on here. So when we use our properties of subtraction, we're going to take the limit of each one separate. So we split them up basically. Now with the first function, the limit of a constant is equal to that value, so that's 5. And this second part is what I was just speaking about. So when you're taking the limit as x approaches infinity of a number over a variable, this is equal to 0. And you end up with 5 for a final answer. The difference with b is what we have to do is we have to take the limit of the numerator and we have to take the limit of the denominator. So when you do this, basically think of infinity like a number in terms of direct substitution. You're going to plug it in. So 2 times infinity is still infinity, and infinity minus 1 is still infinity. So numerator is infinity. For the denominator, when you sub infinity in, you get infinity plus 1, which is still infinity. Now, you can't necessarily make that equal to just 1, like we would if it was 5 over 5, because you don't know the specific value for infinity. So leave it as infinity over infinity. And now what that's going to do is that's going to apply down here, because we have a rule. When we get infinity over infinity, that's called indeterminate form, but it actually does not mean necessarily that you're going to have a limit does not exist. So to resolve this problem, you need to divide every single term in both the numerator and the denominator by the highest power of x that is in the denominator itself. So the function was, this is the one we're going to use again. So it says we're going to finish example 1b since we got infinity over infinity. So it says right here that we are going to resolve it, you need to divide every single term in the numerator and denominator by the highest power of x in the denominator itself. So we have the limit as x approaches infinity. We have 2x over something minus 1 over something. And then we have x over something plus 1 over something. And that something is the same value. And it says that is the highest power of x in the denominator. That would be x to the first. So every single one of these is going to get a denominator of x to the first. And now we're going to simplify. So when we simplify, then we have the limit as x approaches infinity. 2x over x is 2. 1 over x stays 1 over x. Denominator x over x is 1. 1 over x is 1 over x. Now, when we do the limit here, basically you're doing the limit 4 times. You don't need to write it out 4 times, but you certainly can. So you're basically taking the limit. I'll just write it for this one, but moving forward, we'll jump this step. So you're applying the limit as x approaches infinity to every single term in the problem separately. All right, so if we look at all our values here, the limit of the first guy right here, this is a constant, so that equals 2. The limit here of 1 over x, well, that's a number over a variable, so that's 0. Denominator, the limit as x approaches infinity of 1, well, that's a constant, so that's 1. And the limit as x approaches infinity of 1 over x, again, a number over a variable, that is 0. So you end up with 2 over 1, which is equal to a final answer of 2. So 2 is your final answer